Last lesson, you learned about the equivalent circuit model of a lithium-ion battery cell that is known as a Thevenin model. This model has elements that describe open circuit voltage and instantaneous voltage change due to a change in an open circuit due to a voltage drop across an equivalent series resistance R0. And it describes resistor capacitor subcircuits that model diffusion processes inside of the battery cell. In this lesson, we're going to focus on an advanced model that's sometimes found in the literature that contains a circuit element known as a Warburg impedance. The circuit that's drawn on the right side of this slide is known as a Randles circuit, and this equivalent circuit model is derived based on electrochemical principles or by understanding the internal operation of a battery cell using techniques and methods from electrochemistry. In the Randles circuit model, the resistance R0 models the electrolyte resistance. The resistance RCT is a charge transfer resistance that models the voltage drop across the interface between the electrode and the electrolyte in the battery cell that's caused due to a load. The capacitance CDL is a double-layer capacitance that models the effects of charges building up in the electrolyte near the electrode's surface. And finally, the element in the circuit that is drawn using a non-standard circuit schematic diagram and is denoted ZW is a Warburg impedance, and this models slow diffusion processes in the cell. And as you might remember, in the last lesson, we used a resistor capacitor subnetwork to describe diffusion, and here the Warburg impedance, which is something different from that, is also attempting to model diffusion. And so we're going to learn about why this is the case by learning about this Warburg impedance and how it's modeled mathematically. When analyzing and learning about electrical circuits, it's common to talk about the impedance of circuit elements. Now, impedance is a similar concept to resistance, but is a little bit different in fact. Impedance describes the complex resistance of an element, using a complex number, to a particular input frequency rather than resistance, which is some constant value that applies equally to all frequencies. So for example, a capacitance has high impedance to DC but has low impedance at high frequencies, and so the resistance is a function of frequency, or maybe better put, the impedance is a function of frequency. An inductor behaves in the opposite manner. It has low impedance to direct current, but has high impedance to high frequencies instead. Now, impedance has a magnitude component and a phase component, and the magnitude describes the absolute amount of resistance at a particular frequency. The phase component describes how much an output signal will be delayed compared to the input signal for some input frequency in steady state. So it's common to combine these two numbers of the magnitude of the impedance and the phase impedance of the impedance together into a single complex number. And so the magnitude of the complex number is equal to the magnitude of the impedance, and the phase of the complex number is equal to the phase change of the output versus the input signal. So with that in mind, we can discuss the Warburg impedance. The Warburg impedance ZW is modeled as a constant value AW divided by the square root of j omega, where omega is the frequency of the input in radians per second. If we plot the magnitude response and the phase response of a Warburg impedance as functions of frequency, the resulting plots look like those on this slide. The magnitude response of a Warburg impedance looks a lot like the magnitude response of a capacitor, and you might mistake it for that if you don't look very carefully at it. The Warburg impedance also has a high value of impedance at low frequencies and a low value of impedance at high frequencies. But if you open your linear circuit textbook once again, you'll be reminded that a capacitance has an impedance whose value changes with a slope of negative 20 decibels per decade of input frequency, whereas the Warburg impedance has a slope of negative 10 decibels per decade instead. Also, you might remember that a capacitor has a constant phase shift of negative 90 degrees for all frequencies, whereas this Warburg impedance has a constant phase response of negative 45 degrees for all frequencies. So this is different. A Warburg impedance is different from a capacitance, but has some similar properties. And one of those similar properties is that the phase shift is constant over all frequencies, and so we refer to the Warburg impedance as a constant phase element. But because the phase is different from that of a capacitor, we can't model the Warburg impedance with simply a single capacitor. In fact, it turns out that there is no simple differential equation that we can write with standard calculus that represents a Warburg impedance exactly. And this makes precise circuit simulation intractable when our model includes a Warburg impedance. But it's possible to reproduce the effect of a Warburg impedance or approximate the effect using multiple resistor capacitor networks wired in series as shown in this diagram. So that is, we can approximate this impedance ZW using a parallel resistor capacitor branch with values R1 and C1 in series with another parallel resistor capacitor branch R2C2 in series with another branch R2C3 and so forth for any large number of resistor capacitor branches. Now, if we desire an exact perfect equivalence to the Warburg impedance, then we require an infinite number of resistor capacitor networks, which is why simulating one of these circuits perfectly becomes intractable. But it turns out that the effect of Warburg impedance can often be modeled very well over some frequency range of interest using a relatively small number of resistor capacitor pairs. So a capacitor by itself contributes a magnitude response that has a slope of negative 20 decibels per decade, whereas a resistor by itself contributes a magnitude response with zero slope. If we combine a resistor and a capacitor together, the magnitude response has a slope of 0 dB per decade at low frequencies, and then negative 20 dB per decade at high frequencies. And this distinction, the boundary between what we consider low and high frequencies, depends on the values chosen for the resistor value R and the capacitor value C. So by choosing resistor and capacitor values carefully, it's possible to have a slope of 0 for some range and then negative 20 for some range. And we can do that at arbitrary points in the frequency domain, however we like. Similarly, a capacitor has a phase response of negative 90 degrees, constant, and a resistor has a phase response of 0 degrees, constant. And when these elements are combined, we can obtain a phase response that transitions between negative 90 and 0 degrees. And when we put multiple resistor capacitor branches combined together, we can have phase transitioning between negative 90 and 0 and back and forth as many times as we like. So by choosing different values for resistances and capacitance in these branches, we can often approximate a Warburg frequency response really well, in fact, as closely as we like. And the figures on this slide attempt to illustrate this. So in the left figure, you see the magnitude response of the ideal Warburg impedance as this straight line having a slope of negative 10 decibels per decade. And you can also see three different curves that correspond to the magnitude responses of circuits having either 3 or 4 or 5 parallel resistor capacitor branches where the individual resistances and capacitance have been optimized to try to approximate the Warburg impedance, the magnitude response, as closely as possible. On the right figure, you see the ideal Warburg phase response as the constant blue line again at negative 45 degrees. And you also see the approximate phase responses of these three different resistor capacitor circuits. And so you can see that the approximation is never exact in any of these cases, but the example does show, I hope, that with a relatively small number of resistors and capacitors, it's possible to approximate quite closely the infinite order response of the ideal Warburg impedance. So even though the exact equation that describes diffusion in a lithium-ion battery cell which is modeled by the Warburg impedance, cannot be achieved very practically in implementation, you can see that these diffusion voltages can often be approximated quite well using a small number of resistor capacitors in an equivalent circuit model. And so this gives us some hope that the Thevenin model that you saw already has some physical significance and credibility, and that by generalizing the Thevenin model to include more resistors and capacitors, we even have a more credible battery cell equivalent circuit model. So the circuit drawn on the left is the Randles circuit that you saw at the beginning of this lesson. And in the Randles circuit, the double-layer capacitance is often omitted because it has very little impact on circuit performance except at extremely high frequencies. So for the capacitor charges in a very, very small fraction of a second. And if you compare that with the time constants of the diffusion processes, which you've already seen occur over minutes, this double-layer capacitance is often considered to be negligible, and so we can remove it from our circuit diagrams for many applications. So if we do that and think about what's left, then you've got two series resistances, R0 and RCT, which I can combine together into a single series resistance if I like, and that would be the same as what we called R0 in the Thevenin model. So R0 in the Thevenin model takes on the function of both R0 and RCT in the Randles circuit as the instantaneous resistance of this cell. And then if you take the Warburg impedance from the Randles model and you expand that as some small number of resistor capacitor networks, you see that we get the Thevenin model, a generalized version of the Thevenin model on the right-hand side of the slide. So the circuit model we end up with from electrochemical principles turns out to be basically a Thevenin model that has multiple resistor capacitor branches instead of a single resistor capacitor branch. So to summarize what you've seen in this lesson, you've learned an extension to the Thevenin model that you had previously learned about in a previous lesson. And we started by looking at a Randles circuit, which has an electrochemically inspired form. And the Randles circuit includes this new element that we had not talked about previously, the Warburg impedance. And you learned that this Warburg impedance cannot be modeled perfectly with a finite order differential equation. But you also learned that this impedance could be modeled very well for frequencies of interest using a relatively small number of resistor capacitor pairs. So the electrochemically inspired model reduces to a Thevenin model having multiple resistor capacitor pairs, and that gives us confidence that the Thevenin model is a reasonable description of cell dynamics. So that brings us to the end of this lesson, and at this point you've seen a circuit model that describes many lithium-ion battery cells quite well. You've seen equations for this model, some of them in discrete time, some in continuous time, but there's some that we've seen only in continuous time at this point. So we need a way to transfer these equations from a continuous time form to a discrete time form, so ultimately we can use them in our battery management systems. And I'm thinking particularly of the resistor capacitor equations, which we have not yet transformed. So the next subject that we look at has to do with how do I transform these differential equations into discrete time difference equations. That's what we look at next.